So this entry is on applications of systems. So you've gone over solving systems by graphing, solving them by substitution, solving them by elimination. So you have all these methods to solve systems of equations, but now we're going to take those methods and apply them to certain situations in real life where a system of equations would make sense. And we have three separate scenarios that we're going to go over. Each of these are three. In the packet, you have 2 copies of these. That's either in case you make a mistake, or if you don't make a mistake, you could share with a friend or just recycle the second half. But please don't put the second half back into the bin, because then someone thinks they're getting the whole packet when really they're just getting half of the notes. Now, just looking at this first problem, whenever we have a system of equations, we're going to have 2 different sets of information. This one here, this business problem, let's read it out. It says a fashion designer makes and sells hats. The material for each hat costs $5.50. The hat sells for $12.50 each, and the designer spends $1,400 on advertising. How many hats must the designer sell to break even? So we're going to kind of separate this information into 2 separate sets of information so that we can get 2 separate sets of equations, or 2 separate equations. What I see here is I see that they make and they sell hats. So there's a cost to making the hats, and then there's an amount that they get from selling the hats. So let's break that up into our 2 different sets of information. And I'm going to do that using a highlighter, because I think that's the easiest way to see it. So when we think about cost, it costs a certain amount to make the hat, right? So each hat costs $5.50. Now separately, they sell the hats for $12.50 each. So that's different than cost that sell, so that's another set of information. So I'm going to highlight that one, $12.50 each. We also see that the designer spends $1,400 on advertising, so that's actually another cost, kind of a hidden cost. All right, so we're going to highlight that. Okay, and what we're going to do is we're going to take each of those sets of information and we're going to build an equation. So now that I've highlighted that, I'm going to tape it into my book. I want to highlight first and not tape first, because I can't highlight over tape, it just kind of smudges it off. So go ahead and cut out the first problem, tape it into your book, and then we'll start working on the solution. So I want to start by labeling my variables. I'll have X be the number of hats, and Y can be the cost. Okay, it could be the cost to make them, or the cost that she gets from them buying them, right? Kind of like the profit. So we want to figure out how many hats must the designer sell to break even. So at what point does she start to make money? And let's look at kind of the first set of equations we have, which we highlighted in yellow. Okay, each hat costs $5.50, and the designer spends $1,400 on advertising. So that equation would look like Y equals $5.50 for each hat plus the $1,400 on advertising. And then how much she makes, which I highlighted in orange, is she sells a hat, or the fashion designer sells the hat for $12.50 each. So that's Y equals 12.5x. And now I have a system that I can solve. So I think the easiest way to solve this system would be to use substitution. What I can see is in substitution, I'm trying to get an equation solved for a variable so that I can substitute it in. It's really easy with these two because they're both already solved for y. Okay, the y is already by itself. So I'm going to figure out now, right? When does the cost, when does the cost equal the profit? So I'll put this one in for here. And I've got 5.50x. And you don't have to write the 0 if you don't want to. Plus 1400 equals 12.50x. And then I go through solving it. So I'm subtracting the 5.5x from both sides. That gives me 1400 is equal to 7x divided by 7. And x is going to equal 200. So after 200 hats, right? How many hats must a designer sell to break even? Well, 200 hats. So we always want to answer with a statement. So the designer will break even after 200 hats. Now notice it didn't say we had to find y, right? The price or the cost. We just had to find the number of hats. So we didn't have to do all the work here, but we did need a system of equations to figure out the number of hats. And that's it for example 1. Turning the page, let's take a look at example 2. This one talks about the zoo. The local zoo is filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons per hour. When will the 2 tanks have the same amount of water? And explain. So this could be good, and it's kind of a good example of if you have 2 different tanks and you're trying to figure out how much time it's going to take to fill them up to get to an equal amount as part of your job kind of at the zoo, and you don't want to be there just kind of waiting and waiting and waiting. Maybe you can figure out what time, how much time it will take, and then you can go off and then come back. So this is kind of a good real-world example if you were to work at a zoo. So let's go ahead and find the 2 separate sets of information so we can make our 2 equations. The 2 separate sets of information I see are the 2 different tanks we have, right? So we have one water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. So that's kind of one set of information, right? And then we have a second water tank. That would be my second set of information. And that one contains 29 gallons of water and is filled at a rate of 3 gallons per hour. So now I have 2 different sets of information. I can make 2 equations. And I'm going to cut out that problem now and tape it in, and then we'll show the work at the end. Okay, so I've taped it in, and now I've got tank 1. This is my first equation, and tank 2 as my second equation. And I do want to label some variables. So let's let x be time. And it looks like they're talking about hours, so we'll say hours. And y can be the number of gallons. Because it says gallons per hour, so usually we're going to have gallons over hour. It's kind of similar to slope and having a rate of change. If you have gallons per hour, and the rate of change is y over x. It kind of clues you into your y value is probably going to represent gallons, and your x value is probably going to represent hours. So looking at tank 1, it says that one water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. So I know that the number of gallons, it starts at 50, right? And I'm adding 10 gallons for every hour of time. Tank 2, similar, right? It contains 29 gallons of water, and I'm adding 3 gallons of water each time. So now I want to figure out when will those two have the same amount of water. Similar to the other one, I'm going to use substitution because they're both solved for y. I would almost always use substitution if they're both already solved for a variable, because then really what I'm doing is I'm just setting these two things equal to each other, right? Those two expressions. So when is tank 1, which is 50 plus 10x, equal to tank 2, which is 29 plus 3x. And now we're going to go through and we're going to solve that. So variables on the same side, I want to subtract the smaller one. So I subtract 3x from both sides. And I have 50 plus 7x equals 29. And now I subtract 50 from both sides. You get 7x is equal to, and it looks like we're going to have a negative 21. And divide both sides by 7. X equals negative 3. So I have x equals negative 3. So at negative 3 hours. Well, that's kind of confusing, right? Because I can't have a negative amount of hours. So sometimes, and a lot of times when you have applications and systems, some things just aren't going to work. I can't have a negative amount of hours. Therefore, right, and if you kind of think about it this way, if this starts at 50 and is getting 10 gallons per hour, and this starts at 29 and it's getting less gallons per hour, there's no way that they're going to add up to the same amount. So we've proven that algebraically, okay? Because negative 3 is not a valid answer for the number of times. So in this situation, what we would write as a solution is that there's no solution. And the tanks will never have the same amount of water. Or we can just say won't have the same amount of water. So I didn't even have to solve for y for this one because I already have an invalid answer for x. Now, once you get like x equals negative 3, you don't want to jump in right away and say, okay, there's no solution. Always kind of look back at your work and make sure you didn't make a mistake. I happen to just know the answer, so I can tell you right away that there's no solution. If I were doing this problem as you, and I got x equals negative 3, and I saw negative 3 as hours, I would think, okay, before I say there's no solution, let me make sure I didn't make a mistake. And I'd go through and look at each step and make sure I did all my steps correctly. And if I did, I'd double check and make sure that I set up my equations correctly. And if everything was perfect, everything worked out, and x is still equals a negative number, and it's not a valid solution, then I would say no solution. So our last problem talks about airplanes and wind speed and the plane, or the speed that the plane is traveling. And let's read this one out. So a traveler flies from Charlotte, North Carolina to Los Angeles, California. And at the same time, another traveler flies from Los Angeles to Charlotte. So basically, one is going, to one place, the other is going the opposite direction. So we have two different planes going the same kind of distance, but one is going with the wind and one is going against the wind. It says the airspeed of each plane is the same. The ground speeds are shown below. What is the airspeed and what is the wind speed? So that's what we have to find out. Well, an interesting note kind of about planes and wind and really force in general is that when you're in a plane or in a car or anything that's moving and there's wind speed, it's either going to help you, right, or it's going to hurt you as far as how fast you're going. And this comes from physics, different forces acting upon each other and kind of adding up and making what's called force triangles. And you'll get into all of that when you go over physics in either 8th grade or in high school. But if we talk about a plane is either going with the wind or against the wind. And if it's going with the wind, then that airspeed is helping it along the way. And if it's going against the wind, then the airspeed is hurting it, right? It's subtracting from the plane, or the speed of the plane. So we're going to use that information to make our equations. Now, I'm not using highlighters on this one because the information's already broken out for me in the problem itself. So I'm going to use that information to build my system. So now I'm going to label my variables, and it's kind of labeled for me here. A is going to be the airspeed, and W is the wind speed. And when I think about setting up an equation, I want to use the information I'm given. So I know that we have the same plane, right? And that when the plane has, right, the airspeed with the wind speed, then it's going to be going 550 miles per hour. But when it is against, right, when I'm subtracting the wind speed because it's flying against the wind, then it's only going 495 miles per hour. And that's how I set up my system of equations. And I just have to figure out, well, which way is best to solve this one. It looks to me right away that elimination would be the easiest because I have two opposites right here, right? Positive W and negative W. So let's add those two equations together. When I add down, I get 2a, right? Those cancel, equals, and then this is going to be 1045. And then I divide both sides by 2, and a equals 1045 divided by 2 is going to be 522.5. Okay, so the airspeed of the plane is 522.5 miles per hour. Okay, now what about the wind speed? Okay, for the wind speed, I'm just going to take A and substitute it either in here or here, whichever one looks like it's easiest. For me, it looks like the first one's going to be the easiest to use. So when I know A is 522.5 plus the wind speed is 550, then I subtract 522.5 from both sides. W is going to equal 27.5. So the wind speed is 27.5 miles per hour. And of course, we always want to answer with a statement, so we're going to say the airspeed is 522.5 miles per hour, and the wind speed just 27.5 miles per hour. So you're going to see this one a lot. Different things traveling at different speeds. That's a common problem you'll see. Another common problem will be, something including people's age, or something including like the amount of dimes and quarters you have, or tickets sold, or that kind of thing. So there's a lot of different applications of word problems. We just went over a few to get you used to breaking it up and trying to find two sets of information, and kind of the best way to use that set of information to form equations and solve those equations using whichever method you prefer. So graphing, substitution, elimination, whichever one you feel is easiest. So now that you have that in your notebook, next you're going to turn to the practice, and after that we're going to be working with linear inequalities, or inequalities in two variables, and then systems of inequalities with two variables. So it's pretty cool.